Good day, everyone. We are Group 15, and today we are excited to present our project on the production of gasoline from plastics. This innovative process not only addresses plastic waste but also creates a valuable alternative for gasoline. Let's take a deep dive into how this works and the systems supporting it. Every year, the world produces over 300 million tons of plastic, much of which ends up in landfills or the ocean. However, plastics like polythene and polypropylene are made from hydrocarbons, the same building blocks as fuel. Through a process called plastic pyrolysis, we can convert this waste into gasoline and other fuels. Plastic pyrolysis is a thermal decomposition process. That means it breaks down plastic using heat in the absence of oxygen. Without oxygen, the plastics don't burn. They crack into smaller, unusable hydrocarbon molecules like gasoline. This method not only reduces pollution, but also turns a waste product into a resource, making it a win-win solution. The first step in this process is collecting the right kind of plastic waste. The raw material is known as feedstock. Not all plastics are suitable. For instance, PET, which is used in water bottles, and PVC, used in pipes, release harmful gases like chlorine when heated. So, we mainly focus on non-halogenated plastics such as polythene used in shopping bags and polypropylene found in food containers. Collecting clean and appropriate feedstock is crucial. If poor quality plastics are used, the final fuel will be contaminated. Sources of feedstock include household bins, industrial waste, dump sites, and recycling centers. Once collected, the plastic is carefully sorted. We remove items like PVC, food waste, metals, and even bottles, labels, and leftover oil. These impurities could lower the fuel quality or damage equipment. Just like how good ingredients make a better meal, clean and sorted plastic leads to cleaner fuel and more efficient processing. After sorting, the plastic is thoroughly washed to remove dirt and oil. Then it's dried using hot air dryers. Why dry it? Imagine trying to grind wet plastic. It sticks and clogs the machine. Also, moisture can cause corrosion and lead to dangerous pressure buildup in the reactor. Shredding. Now comes the shredding process. The plastic is cut into small, uniform flakes. This increases the surface area, which helps the pyrolysis process occur more evenly and efficiently. Think of it like cooking. Smaller pieces of food cook faster and more evenly. The same logic applies here. The shredded plastic is then loaded into an air-tight reactor. Heating begins slowly, typically between 300 to 500 degrees Celsius, with the help of catalysts like zeolite or fly ash. Why no oxygen? Because we don't want the plastic to burn. Instead, we want it to break apart or crack into smaller molecules. If oxygen enters, it causes combustion, resulting in ash and smoke. As the plastic melts, it releases hot vapors containing different hydrocarbons. Carbon 5 to 12 range becomes gasoline. Carbon 13 to carbon 20 becomes diesel. Lighter gases like methane may be used to heat the reactor itself. The vapor pass through condensers where they cool down. Heavier vapors turn into liquid fuel, while light gases stay gaseous or are reused. Fractional distillation. The liquid mixture from condensation still contains different fuel types, so we use fractional distillation, just like in oil refineries. We reheat the liquid, and gasoline, which boils between 40 and 20 degrees Celsius, rises and is collected. This gasoline is then stored separately for use. Support units. A successful plant doesn't only need reactors and condensers, it requires several support points. Control rooms to monitor everything in real time, storage areas for feedstock and finished fuel, administration buildings for staff, boiler house for steam, and loading bays for trucks to deliver and pick up products. It is a very full-scale operation that mimics the structure of a small refinery. Computer and sensor needs. Modern plants rely heavily on computer systems and sensors. For example, temperature sensors ensure the reactor stays within the safe operating range. Pressure sensors prevent accidents by detecting pressure buildup. Level sensors monitor how full tanks are, avoiding spills. Gas analyzers check emissions to make sure we are staying environmentally compliant. All this data is sent to the central systems like SCADA, supervisory control and data acquisition, allowing real-time monitoring and control. Output and safety devices. To visualize and interact with this data, we use monitors in control rooms, electronic display boards in the plant, alarms and sirens to alert for danger, and printers for reports. Valves and actuators also help automate the physical flow of materials, opening and closing based on real-time conditions. System software. The entire plant runs on several types of software. SCADA and PLC software for controlling the process. ERP systems like SAP or Oracle for managing finance, HR, and inventory. LIMS for quality control in labs, CMMS to schedule equipment maintenance, and security software like facial recognition and badge access for protecting sensitive areas. Connectivity and topology. To connect to all these systems, we use different network types. Wired Ethernet for reliability in the control room, Wi-Fi for handheld tablets and mobile inspection tools, cellular or internet for remote monitoring and cloud backups. The network is designed in star and ring topologies, combining performance and redundancy. That means even if one connection fails, another route can take over. In summary, turning plastic waste into gasoline through pyrolysis is a powerful solution to two major global problems, that is, plastic pollution and fuel shortages. It's efficient, clean, and supported by advanced sensors, softwares, and systems. With this technology, we can reduce waste, generate fuel, and create jobs, all while protecting the environment. Thank you for your attention.